We just starting a regular colloquium of regular series, and today's speaker is Robert Cava from Princeton University, and you already read about him in the announcement because Sergey wrote a lot of his credentials. I will just simply say kind of few words because I know him for a long time already. He is actually the leading specialist and probably the main person in the world in making new materials and also studying them, not only making, not only preparing, but studying them. So, and he worked and he makes material in actually all whole field of solid state physics. It may be superconductors or maybe very recent some new topological insulators or wire semimetals. In all of these fields, he was one of the persons, and very often he actually not just joined this new direction, but created new direction, new fashions. Now, as you read, he is actually already for a long time a member of American National Academy of Science, but also a member of a British Royal Society, very prestigious and very old, probably the oldest scientific organization in the world. And he got numerous prizes for many countries. That's what you also saw in the announcement. So, the most incredible number, he has 100,000 citations in Google Scholar. I never saw anything like that, but that simply just tells you how strong impact his work has on the community. Now, a couple of words about biography. Early years probably is not so important, but what's important that almost 20 years from 1971 to 96, he worked at the Bell Laboratories. That probably was at the time the best, the strongest team in solid state physics, both in theory and experiment. We in Russia and Soviet Union had very strong theoretical physics, for example, like Landau Institute or some other places. But such combination, when in one place you have also, strong theory, but also very strong experiment, that was probably unique at Bell. And there were many Nobel Prize laureates working at Bell at that time, maybe a bit earlier, John Bardeen and Shockley and Phil Anderson and many others. Now, after Bell was dissolved, actually, Robert moved to Princeton University from 96. And from 96, he is professor and head of the big group in Princeton University. It's also not a bad place, of course, because you remember probably that Einstein, in Russian we pronounce it Einstein, he was a professor in Princeton University, and they even created a special institute when he came there, Institute of Advanced Study, one of the first institutions of this kind in the world. So we are really very glad that he agreed to give a talk here, and all the more so that in New Jersey, when Princeton is located, is now 7 in the morning. So, okay, but I hope that it will be okay, despite some maybe technical problems, but hopefully it will be okay. So please, Bob, go ahead.
Thank you, Daniel. Yeah, Daniel and I have been friends for a long time, and we're interested in the same things from a different side. And obviously, I've always really very much respected Russian theorists, and it's a lot of fun for me to be able to give this talk. You know, it's my first talk since January or February of this year, so I don't know how long it's going to be. And one thing about me is I talk too much, so you have to make me stop. You guys have to stop this at some reasonable time, okay? And so the first thing we'll talk about is, as Daniel said, you know, I'm not a materials physicist. I find materials that I hope are interesting to physicists, and I try to do some interesting chemistry, but the point is primarily to make things that might have properties that you find interesting. And I know that some of them are not going to be interesting and some of them are, and it's almost like being a salesman and trying to sell the things that we do to people who like to do the real interesting physics on them. So here are some of my graduate students shown on this, the bottom of this thing. Most of them have graduated and moved on with their life, but Loy is still with me. And you'll see that's Loy on the end there. Let's see, there's a way to use a pointer. Can you see the pointer? Yeah, this is Loy here. Can you hear me talk? Okay. First, we'll talk about geometric magnetic frustration. So the point is, the joy is that you can make many materials in the world where you can put magnetic atoms on the vertices of triangles or tetrahedra. And depending on the atoms that you put on the vertices and the way the triangles are shared, you can get many different variations of magnetic interactions that are frustrated. And you can either have the plaquettes have to spin zero somehow if they have antiferromagnetic coupling dominant, but you don't know how many plaquettes you need to put together to get zero spin. That's when life gets interesting. And here's a picture of a Kagame basket and something about how the pyrochlor lattice is related to the Kagame lattice. You just take this Kagame, which is corner sharing triangles, and you put a vertex on the top of every triangle, and you get a tetrahedron, and then the tetrahedra share corners to make a pyrochlor. So long ago, we figured out that a pyrochlor has two interpenetrating sublattices, and you could, if you consider only the metals, you could put magnetic metals on either one sublattice or the other sublattice. But the whole deal about solid-state chemistry is seeing an overall structure and then trying to get atoms to substitute in a way that gives you something different while maintaining the same basic crystal structure. And you can do that with, and you can directly test the relationship between rare earths on a pyrochlor lattice and rare earths on a Kagame lattice by adding an extra atom, which forces this lattice here, which is the pyrochlor, to become a Kagame by putting non-magnetic atoms in between every set of magnetic atoms. So instead of having the magnetic atoms infinitely connected, you separate them. And you can it's difficult to do this, but you can put the same rare earth on the Kagame lattice and the pyrochlor lattice, and then just test which one is more frustrating. Okay. So the whole trick, as usual, is to see the forest through the trees. So the normal way of looking at solid-state chemistry is to draw the coordination polyhedra. That's shown on the left side here. And if you extract the magnetic part of this lattice, you put rare earths on these sites that have the cubes. If you put a rare earth inside every cube, which is where they sit, then you get this thing, which is a Kagame lattice here. And the relation between Kagame and pyrochlor is easily seen in this depiction of the crystal structure right here. So the idea here was to try to find a set of rare earths that would make both crystal structure types. So there's a stability region for the Kagame, and there's a stability region for the pyrochlor. And if you want to do a direct comparison, you have to find a rare earth system that is stable in both structures. And it turns out to be there aren't too many of those. And neodymium is the best one, believe it or not. And so we can directly compare the neodymium scandium niobate pyrochlor with the neodymium antimony magnesium Kagame. And then you can plot, you can make both of them, and you can make them both pure, and you can plot on a single curve the magnetic susceptibility versus temperature, which is shown on the left side here for these two things. And as usual, you see a very low interaction temperature, fraction of a Kelvin, which is not good. We'll see more about that later. And the magnetic moments are very similar. And the only thing that's different is if you look at the specific heat, you can see that the pyrochlor lattice loses its magnetic entropy over a broader range of temperature and at a lower temperature than the Kagame does. So adding that extra vertex makes things order at an even lower temperature. So this is like 400 millikelvin or something like that. It's a very low temperature. It's very annoying. It's so low. So part of the fun I have in life is talk to theorists. I like them a lot. And these three theorists on separate occasions said to me the same thing in different ways. They said, rare earth pyrochlores are fun, but there's the interactions between rare earths are so small that you have to do extreme experiments to get them to observe the properties of these pyrochlore lattices. Can you make me a pyrochlore with a stronger magnetic interaction than 1 Kelvin? So that's a good chemical challenge. And you have to realize that if you have a rare earth, the interactions are going to be very, very low. The effective magnetic interactions will be low because these are F electrons, which are close to the core of the atom. And so they're not going to be good for interacting with each other. If you want to have strong interactions, you have to go to transition elements. And so you need to put transition elements into a pyrochlore lattice. And to do that, you have to look at the other side. Let's see, I have a picture of it here. Yeah. So the pyrochlore is two interpenetrating lattices of tetrahedra, but the tetrahedra in one case for the lanthanides are made of 7 coordinates with oxygen, and the other ones are 6 coordinate with oxygen. And the 6 coordinate with oxygen can then be a transition metal. And once you can put a transition metal there and a non-magnetic atom on the other side, you can get the interactions to be dominated by transition metal magnetism, which is hundreds of degrees, can be 100 degrees instead of 1 degree, because they're 3D based, not 4F based. And then you have to get charge balance you have to be able to make something where you balance the charge. So if you have a divalent transition element, which has a high magnetic moment, then you can't make a pyrochlore anymore out of oxygen. You have to use fluorine. And so that's the principle. The trick is, how do you do it? And then I had this character here, Jason, who was one of my graduate students. I remember one day said to me, I want to make some of these fluoride pyrochlores you're talking about, but I need to buy a tube, a metal tube. So this tube right here. And the reason he needs to buy like a nickel metal tube is because nickel doesn't react too much with fluorine. And he needed to do an in situ HF anneal, hydrofluoric acid, anneal, hydrofluoric vapor to clean out the fluoride precursors. So transition metal fluorides are really kind of a disaster when you get them from a chemical company. They're mixed with all sorts of organic goop that they use to create the fluoride. You have to get the organic goop out or this doesn't work. And the way you do that is you heat them in HF, which is not a pretty thing to do. This kid, the rest of my grad students thought he was going to kill everybody. I thought he wasn't going to kill everybody, but he didn't kill anybody. And he made crystals. And here are Jason's fluoride pyrochlores based on cobalt 2+, and nickel 2+ here. And they grow nice big crystals in the floating zone furnace. Here's a picture of the floating zone furnace. So after you figure out how to get the fluorides clean, then you have to do a mixture with other fluorides to make it work, make the charge balance work. And these things are spectacularly frustrated magnets. And so this, when you plot 1 over the susceptibility versus temperature, if you get a straight line, which you get here, let's look at this one. You get a beautiful straight line, and then at low temperature, something strange starts to happen. And that's an indication of first of all, the intercept of this line tells you the interaction temperature. And then this temperature right here tells you that's when the spins are starting to do something and make them deviate from the Curie-Weiss law. So these fluorides are kind of exactly what the doctor ordered. They have interaction temperatures of 100 Kelvin now with big magnetic moments. You grow giant crystals in the floating zone furnace, and you can then study frustration on a pyrochlore lattice at a humanly accessible temperature, which is a few Kelvin, not a few millikelvin. And of course, you noticed already, I suppose, that to get the charge balance, we had to mix sodium and calcium or sodium and strontium on the non-magnetic rare earth site. Now that introduces disorder because sodium is +1 and calcium is +2, and you need to do that to balance the charge. But it introduces some kind of disorder on the lattice next to the magnetic lattice. And depending on how strongly that disorder interacts with the magnetic interactions on the cobalt sublattice, it'll give you either a negligible effect or something. And in fact, I think that the reason that these things order at all to make spin glasses is because of this random distribution of sodium and strontium or sodium and calcium on the neighboring sites. So they are spin glasses, but we think that you get a spin glass, the classical spin glass behavior, which you can trace with this kind of thing where you change the frequency of the magnetic field and then watch the relaxation rate change. And, that's the classical case of a spin glass. And the only reason these do it is because you have disorder on the A site, the off site thing. Otherwise, they could get very, very cold before anything happens. Okay, they're already 1/100th of their interaction temperature, which is a civilized rate. All right. So I was interested in geometric magnetic frustration, and along came some nice theory work on honeycomb lattices. And it turns out that honeycomb lattices are much more common in solid-state chemistry than Kagame lattices or pyrochlore lattices are. And so I was interested in trying to understand why people got so excited about these quantum spin liquids, about why the honeycomb lattice was so interesting. And I guess it's the original experimental work, at least, was on Na2IRO3, which is a very difficult material to make or work with. And from an experimental perspective, if you want to work on a honeycomb lattice with strong spin orbit coupling to give you some kind of magnetic interactions that you can get a good model for, you can't grow crystals that are very big. So all the iridate crystals that are known of this Na2IRO3, which if you remember from 10 years ago when that first appeared, they are sub-millimeter in size. So you can't really do good experiments on that material. The reason people get excited about that is that there's a normal kind of magnetic coupling between neighboring atoms, which I guess is Nail type or something. But then there's an additional term that's called the Kitaev term, and I guess he's a Russian theorist. I don't know if he lives in the States or in Russia or what, but there's an additional term that is frequently masked by the other interactions. But you can write an exact, you can solve exactly for what you expect the magnetic system to look like if you have those kinds of interactions as the dominant interactions on a honeycomb lattice. So that's why it's so interesting to everybody, as far as I can tell. And first, the sodium iridate was the first experimental system that did it. It has terrible crystals, so it lived out its time and didn't do anything too exciting experimentally. Then came ruthenium chloride, which became more interesting because that one also has a honeycomb lattice of ruthenium. And ruthenium is a 4D element, so its spin orbit coupling is less dominant than in the iridium case, but you can grow big crystals of ruthenium trichloride. So you can actually study this material. And some people at Oak Ridge in the States made kind of a career out of working on ruthenium trichloride. And you can change the ratio of the normal magnetic interactions on the honeycomb lattice to these Kitaev interactions by applying a magnetic field. And so somewhere around 8 or 10 Tesla, which is a ridiculously high field, but it's not so ridiculous that you can't get to it in the laboratory, you switch from the dominant antiferromagnetic interactions to this dominant Kitaev interaction, and you can observe a quantum spin liquid, or so it's argued. Okay, so that's good. But you notice that that's a high field. And one reason I love to go to conferences, and I miss them immensely, and I hate Zoom talks, is that, that you miss the hallway kind of interactions that can be very, very informal and very productive. And I think I was at Daniel's 80th birthday party in Dresden when a theorist stopped me on the way to the cafeteria and said, why don't you characters make these honeycombs out of cobalt instead of iridium and ruthenium? So I remembered, we had worked on cobalt honeycombs forever, and I knew that cobalt was a good atom to put in a honeycomb lattice. So I came back from this meeting and I said, well, let's try to make some cobalt honeycombs. And this postdoc here, Riden, who's now in China, who came from John Tranquatta's group at Brookhaven, who knew something about neutron scattering. That's what they do at Brookhaven. And John is a great neutron scatterer. I said, can you make some honeycombs out of cobalt? Well, first she worked on ones that we had worked on, and then she started putting things together, and she found that barium, sodium 2 cobalt phosphate didn't make a honeycomb, but it made a triangular lattice. So now these blue octahedra, this is a new compound never before discovered, and these blue octahedra contain the cobalt, and when you look at them, when you look down on this plane here, it's a triangular lattice of cobalt. And they are not so close together that they are forced to magnetically order at a high temperature. So the problem with a lot of these oxides is that when you couple the transition metals too strongly, then they will magnetically order at some high temperature. No matter what, they'll find some dominant magnetic interaction, and they'll do something you don't want them to do. But luckily, these are far enough apart that they don't couple directly, and then you can get some kind of unusual magnetic state, and you can grow large crystals of these things from a flux. So these are millimeter squares. This is what in my world constitutes a large crystal. If it's bigger than a millimeter, that's big. Okay. Next. So then they did some neutron scattering and some elementary property characterization. And it turns out that down to 50 millikelvin, there's no glassy transition and there's no magnetic ordering. So this sodium 2 barium cobalt phosphate looks to me like it's doing exactly what everybody wants cobalt to do, except it's a triangular lattice. It's not a honeycomb, but triangular lattices are not so bad anyway. And, cobalt is a bizarre 3D element. So I guess I was trying to look that up, but I recommend you look it up too. So, in the transitional series, we always say that the orbital contribution to the angular momentum is quenched for the 3D elements because the interactions with the ligands are too strong. But cobalt is an outlier. It has a strong spin orbit coupling term added to its magnetic moments. So, cobalt is a bizarre case anyway, and I think it's just been ignored for too long, but that's my personal opinion. And there are some interesting characteristics that they found. Nobody has been able to give me a real objection to anything about this material. I'm happy to hear it. One thing I'm not happy to hear is an objection when some physicist tells me there are too many elements in that thing. Cut it out. Well, okay, there are a lot of elements there, but the interesting ones is just the cobalt and the oxygen, okay? The rest of them are just spacers, okay? Anyway, so that then led us to this, that material then led us to this old honeycomb lattice material, barium cobalt arsenate. This one has one fewer kinds of atoms in it, so maybe physicists would like it. And it has a honeycomb lattice of cobalt oxide again. So now we have this nice cobalt oxide honeycomb. That's what these things are. I'm showing you with the cursor. I hope you can see it. And, and it's been around since the 70s or something like that. And this very nice neutron scatterers worked on this. Daniel may remember Rosamignon, but maybe the young people in the audience don't remember him. But, it's got a nice layered honeycomb lattice of cobalt. And does it have exotic properties? Yes, it absolutely does. In fact, it's a really bizarre case. And to me, this one looks like a quantum spin liquid. So my colleague Paul Ong got very excited about this material because he measures the thermal conductivity, temperature-dependent thermal conductivity. And thermal conductivity is actually important in insulators because what carries the heat in an insulator? Well, magnetic excitations and phonons, right? So if you go down to a really, really low temperature, if you see some bizarre behavior in the magnetic field dependence of the thermal conductivity, then that's indicating a dramatic change in the heat transport by magnons. And so what Pon found and the students found is that 4 Kelvin, which is not ridiculously low in temperature, at a field of 0.5 Tesla, which is not a high field at all, the magnon contribution to the thermal heat capacity goes away. So the magnons are gone. So a phase diagram can get put together that looks something like this. So this shows the temperature field phase diagram for barium cobalt arsenate with the honeycomb lattice of cobalt. And at 0.5 Tesla, the normal antiferromagnetic interactions go away. So this looks like, to me, or to most people, well, if you care to think about it, that it's become a quantum spin liquid at 0.5 Tesla below 2 Kelvin. So that would be a good thing. Now the problem here is, although this is a very simple material and you can grow crystals of it, I think this field got too crowded too fast, that too many people claim to discover a quantum spin liquid. So there are too many trees in the forest, and maybe any particular tree doesn't become visible. But this is an old tree, so there's a lot of old nice neutron scattering data on this barium cobalt arsenate, and there's more data coming. So this might be a good one. Okay, that's that. Let's see. There's not much of a segue there, except that, we're worried about transport and entropy and stuff like that. And so now I'm going to talk about another class of materials. I talk too much. Okay. This one is high entropy alloys. And the interesting thing to me about high entropy alloys is that, it's not breakfast time for you, but that normally when you calculate everybody knows that the free energy of formation for any substance depends on an enthalpy term and an entropy term. But most often, the entropy term is not even calculated because most substances which have entropy, the entropy comes from lattice vibrations, which are all about the same. So basically, it doesn't have that much of an impact. Or, you can calculate delta H, but it's hard to calculate delta S. And DFT calculations calculate delta H at t equals 0, so there's no delta S term. But it turns out that there are some substances that are stabilized by a large entropy of mixing, and that's what high entropy alloys are. They are substances that are stabilized by high entropy of mixing of their constituents. And it turns out that this is a new field in metallurgy that's been studied for the last 10 years or so. And these high entropy alloys, which have roughly equal proportions of multiple constituents, have mechanical properties that are substantially different than those of a conventional alloy. Let's take carbon steel or something like that, where you have a small amount of carbon in iron and you get a different kind of mechanical character. These things have a dramatically different character. So again, of course, I was sitting at a conference and I saw some metallurgist give a talk on this, and I said, well, I wonder if there's any high entropy alloy superconductors. Well, yes, there is one. Tantalum, niobium, hafnium, zirconium, titanium, many elements there. Niobium and tantalum are BCC, hafnium and zirconium are FCC, titanium is HCP. These are normal kinds of crystal structures for metals. When you mix them together in roughly equal proportions, you get something that is body-centered cubic, which is a BCC. And basically, the way to think about these high entropy alloys is you've stabilized a high entropy structure type with atoms in it that don't normally take that structure type. And it's like a glass on a crystalline lattice. That's how I think of it. It's glassy in that there's a lot of different atoms mixed in there, but it's a crystal lattice in that it's a regular array of atoms. Okay, blah, blah, blah. An important thing to do is when you have all these atoms in the pile, why don't they just form some nanoscale precipitates where two of them get together and do something interesting, and the rest of them just sort of sit there? Well, they don't. And so here's Jing Tao, who's an electron microscopist at Brookhaven. I made her take a look at these high entropy alloy superconductors, and sure enough, there was no sign of any nanoscale precipitates in there where two of these atoms have picked themselves out to form a fine scale precipitate in the alloy. So this is a uniformly disordered alloy with 5 elements in it. And then you can do stuff like plot the electron count variation of TC by changing the ratio of the constituents, and you discover that your high entropy alloy superconducting transition, depending on the electron count, is somewhere in between what you get for a real amorphous solid and a crystalline solid. And then you can look at the upper critical field as a function of temperature, and look at that as a function of composition of the alloy. Well, let's not worry about this because I don't have too much time. And then blah, blah, blah. Yeah, so here's the thing that bothers me. So when you think about a glass, why does it matter? Why does, if the properties of matter are determined by the Fermi surface, why does it matter what atoms give me that Fermi surface? And it can only be that the electron-phonon coupling is what matters. But why does an alloy that has 33% niobium in it, or in some cases 20% niobium, why does it have a better TC than something that has 20% vanadium? Why does it matter? Like, how does the 20% of niobium wag the dog, as we would say in England? How does that make the TC so much higher in the niobium case than the vanadium case? I don't get it. So I guess the point would be that, if you have like a BCS superconductor, which these things presumably are, you have a sea of phonons and you have a sea of electrons, and somehow the coupling between the phonons and the electrons is stronger when there's niobium in there instead of vanadium, something with the same number of electrons. I find it curious. Okay, blah, blah, blah. We're going to go some more. Here's something I like. So these are two scientists in Beijing. In the States, we used to be able to collaborate with Chinese scientists. I don't know if we can anymore. I don't know if you can in Russia, but I'm not sure we can. But, these are two ladies that work in Beijing, and they work in this lab of one of my old friends, Ziyek Zhao, who, and this is a lovely laboratory, and their job is to squeeze the hell out of stuff and break diamonds and see if they can see what happens. And so they put some of my high entropy alloy superconductor between two diamonds, and they squeezed it. And what does it do? Well, first clue is, first of all, if you're making these high entropy alloys, the reason that metallurgists were so interested in them in the first place is that their mechanical properties are remarkable. So I thought, well, maybe you could put these under pressure and they will survive high pressures. And if they can survive under high pressure, maybe they'll do something interesting. Maybe the superconducting ones will do something interesting under pressure. So what happened is, when Jing and Li Ling put this high entropy alloy under pressure, they found that the TC went up dramatically first, and then it stayed superconducting up to 200 GPa, which is a ridiculous high. That's 2 megabars of pressure. And I eventually got them to measure pure niobium and pure tantalum, which do something different. And so the high entropy alloy, even though it looks similar even though you might say, well, it has tantalum or niobium in it, and so it must be the same as them. It's not the same as them. It's something different. So its TC continues to go up, and it's still there at 200 GPa. Now, I was looking at this, and when I was sitting in the science library one time, waiting for the classroom to get empty, and I happened to be sitting in front of the geology books, and I found a geology book that said that, I wanted to get a scale for what pressure 200 GPa is. This is a pressure of the outer core of the Earth. So this stuff is continuously superconducting between 1 atmosphere of pressure and the core of the Earth pressure. So it's unlike, obviously, room temperature superconductivity in lanthanum hydride made with a laser at 200 GPa is exciting, but it's not continuously superconducting. This stupid stuff is continuously superconducting from Earth, and if you can launch it onto Jupiter or something like that, you still have a superconductor. Okay. Anyway, and these people are crazy. They can even measure HC2. Okay. Now, another thing about superconductivity, by the way, our ace in the hole, and a lot of these things is this Weiwei. Weiwei is an excellent materials chemist, and she does crystallography. She did a lot of our good crystallography here. I have to stop talking. But let's talk about what Weiwei, Elizabeth, and Tomas found. Okay, and these are chiral non-centrosymmetric superconductors. Okay, so superconductivity in the BCS picture is just a sea of electrons that interacts with the way I look at it, it interacts with a sea of phonons that come from some crystal structure. But then, if you have a non-centrosymmetric crystal structure, you have K and minus K in reciprocal space not equal to each other. I always think of reciprocal space. You might think as K space, whatever, but they're not the same. So the pairing has got to be different in something that's non-centrosymmetric. But there's more to it than that. And I'll tell you the story of how we found this one. So this is an interesting example of what we do for a living and why I find referees so annoying. Because, basically, here's what happened in this case. If you take, back when MgB2 came to be, I realized that there might be something interesting about magnesium combined with other elements in the periodic table that people don't usually compare it with. And we found this magnesium carbon nickel 3 anti-perovskite. So it's a normal, it's like a perovskite, but nickel is here instead of oxygen, or oxygen is typically here. This is nickel. Oh, sorry, duh, stupid me. This green stuff is nickel. So it's where the oxygen is. So the nickel, which is D8, is accepting electrons. So that's kind of cool chemically, that you take something that's normally a metal, instead of it giving up electrons, it accepts electrons. So I tried to think what other things with this structure type would be interesting. So the whole story here is that you want an electropositive element to put here, an electronegative element to put here, and then a small element to put in the hole. In this case, it's carbon. So a typical thing to put in a hole could be carbon or boron or beryllium. We don't work with beryllium, but carbon or boron or nitrogen could go in a hole. And a typical electropositive element would be like magnesium or rare earth or something like that. Another electropositive elements are something like tantalum. It's very electropositive, meaning it really likes to donate electrons to things. So I thought tantalum, rhodium-3, boron should be a superconductor. Duh. I mean, that's basically the whole logic that went into that, because it has electropositive element, something under something that might accept electrons in a polar intermetallic compound like rhodium. And then maybe you could put something in this hole right here. So we tried to put boron in this hole to make a superconductor out of tantalum, rhodium-3. And sure enough, boron went in the hole and it made a superconductor. Oh my God, so it worked. No, it didn't quite work because the superconducting signal was 2 orders of magnitude too small. So something was superconducting in this sample, but not the main phase. Even though the boron went in there to make tantalum, boron, rhodium-3, like magnesium, carbon, nickel 3, it's these little pattern peaks in the pattern that are very hard to get anybody to pay attention to, that were the superconductor. That's very annoying, but there it was. And do I have this thing yet? My graduate student who worked on this said, you know, many samples later, she complained all the time, I made her do too many samples, but we ended up with pure phases of tantalum rhodium 2b2 and niobium rhodium 2b2 that were purely superconducting. And here's the powder diffraction pattern, which is what we use to find them. And that other phase is completely gone now. Here's where we started. Here's the X's mark the superconductor, and not the superconductor. And the little grass is the superconductor, but then we can make the grass grow. And there was a lovely surprise about this, which Weiwei figured out, which is that they are non-centrosymmetric and they are chiral non-centrosymmetric, meaning that not only do they have no center of symmetry, but they have a handedness. And what I realized in looking back at the literature on superconductivity is that although it was appreciated that non-center of symmetry was significant, the fact that there was chirality was not really appreciated as something. So if you look at it, there's a honeycomb lattice of one set of atoms. There's boron dumbbells, which are cool for chemistry. And then there's these things here, which are spirals of the tantalum. So that's a screw of tantalum, a 3-1 screw of tantalum. And that chirality is maintained. So unlike some structures where you have a screw going one way and then the one next to it goes the other way, these all go in the same direction. So the thing is a chiral lattice. And so those are the rhodium ones. And a big trick, which I hope to transmit, is that you often want to abstract. The crystal structure can look complicated and crazy. And you look at it, you go, I don't understand what that's going on there. But you can abstract parts of this crystal structure so that you understand what's happening. And then if you make a simplified drawing, which is what this is, you can see that the original superconductor, which is actually here, the rhodium one, is made up of blocks that go 2 blocks and 1, then 2 blocks and then 1. And then you could, so once you can separate it that way, a basic principle of solid state chemistry is if you can identify building blocks, maybe you can put them together in a different way. So here is 2 and 1 and 2 and 1, and here is 1 and 1 and 1 and 1 and 1 and 1. And this is tantalum iridium 2b2. This is tantalum rhodium 2b2. These are also non-centrosymmetric chiral superconductors, and they have some minor bizarre characteristics. And until we can grow crystals of them, which is a very annoying thing, of a big enough size, physicists are not going to be able to study them to show that they're really interesting. But they do have a clue that there's something bizarre about them because their upper critical fields at t = 0 exceed the Pauli limit. So the Pauli limit is something that says if you apply enough field on a superconductor, you should break up the pairs, the superconducting pairs. And if you apply more than that, then you have something exotic. Okay, so you can ignore this. I'm happy to have you ignore it if you want to. But, you know, do you really think that the chirality of the crystal structure has nothing to do with the superconductivity? Maybe it does, maybe it doesn't. So we can have triplet or singlet superconductors. And when you have no inversion, you can't simply describe something as a singlet or a triplet. But once you have chirality, I don't know what happens. Here's the list of some non-centrosymmetric superconductors, some of which we found. And here's some chiral non-centrosymmetric superconductors, which are known, but nobody noticed that they were chiral. Okay. All right, now I think do I want to tell you about gold? I want to move to oxides. I think I was told that I'm allowed to talk too long at the Russian seminar. You guys can keep awake. So gold is a bizarre element, by the way. Bizarre because gold is a metal, and you wear it. You know, you wear it on your hand if you're married or whatever. It's an inert metal, so it doesn't react with the atmosphere. But gold is odd. Gold is odd, especially because its electronegativity is odd. You think of it as a metal, but its ability to take electrons is about equivalent to some of the atoms in the periodic table, which you don't believe are metals at all, like selenium, tellurium, and sulfur, you believe that these three things are going to accept electrons in a chemical bond. And you're going to think that gold is going to donate electrons in a chemical bond, and that platinum is going to donate electrons in a chemical bond. But in fact, the ability they have to absorb electrons is about the same as these things that you always think of as absorbing electrons. So, you know, gold is an interesting case. And I know that Sergey and Dale have noticed this too. So this is a nice paper by one of the few solid-state chemists that's also noticed that gold is interesting. And so gold could act like a gold minus instead of a gold plus. Not only can it give up an electron, it can accept an electron. So what I wanted to do was to make some compounds where we tried to confuse the gold and not tell it what to do. So you can put it with an electropositive element, meaning something that definitely wants to give away electrons, in which case gold should take it. So like cesium gold is a famous case of something where gold is gold minus. So you want some very electropositive element in there. And then you want I want an electronegative element in there like bismuth, which would accept electrons from gold. So I wanted to confuse the gold by having it not know what to do. So it wouldn't know whether to take electrons or give them away. And in fact, the first new substance that we made were rare earth gold bismuthides. And those turned out to be not interesting because the gold picked what it wanted to do and it did something boring. It donated an electron. So rare earth gold bismuth 2s, the gold donates an electron, so it's kind of boring. And they're typical magnets, and you know even solid-state chemists can do electronic structure calculations nowadays. So don't ask me to respect people who know how to do that. Sorry. And then we have another thing that's at play here, which is the 18 electron rule. So you know, if you grew up as a chemist, you know that there's the 8 electron rule, which is I can fill the shells in all my atoms if I can count to 8. And then when I have transition elements involved, if I can count to 18, I can fill all shells or empty all shells. And so I don't need a DFT calculation to tell me what's going to happen if I put atoms together and I count to 8 or 18. So that's all good. There they are. So if you make these combinations and you get 8 or 18, you know what you're going to get. You're going to get a semiconductor. And you're going to get a difference between filled states and empty states. Easy. So we tried to make some 18 electron compounds. This is going somewhere, don't worry. So let's look at some 18 electron compounds: lithium, gallium, germanium, zirconium, beryllium, silicon, and scandium, gold, silicon. They are hexagonal, but they do something bizarre. So let's look at this. This is like a honeycomb layer that has alternating two kinds of atoms that alternate. And sometimes these atoms the metal atom, the metallic element in this case is germanium, bonds to the non-metal, which is gallium, just across the layer. So they're just connected. Sometimes they're just disconnected, but sometimes they are partly connected and partly disconnected. So that's a bizarre thing. And the way that happens is in gold. My God, gold, really? So we made some 1-1-1 phases with gold. And I tried to confuse the gold. And so here we use gold, lanthanide, which is a nice electropositive element, and antimony this time, and instead of bismuth. And now antimony is a little bit more, is different from bismuth. It's in the same column of the periodic table, but it's different. And so now we made this compound, which is lanthanum, gold, antimony, and this stupid thing, we have this kind of bond between the golds. So the golds are on top of each other, and they are staggered. So there's not a continuous chain of gold here. There is a discrete gold-gold dimer. Why is that? Where'd that come from? Well, if you look at lanthanum gold tin, so now we're going to compare lanthanum gold tin to lanthanum gold antimony. You don't have the periodic table memorized, but tin and antimony are right next to each other in the periodic table. Antimony has one more electron than tin. So lanthanum gold tin has 18 electrons, and it's a semiconductor. And it has this crystal structure over here where every gold is bonded to a tin. I'm sorry about the picture. Every gold is bonded to a tin. And, it's just a normal 18 electron compound, and it's a semiconductor. But lanthanum gold antimony has 1 electron more, but something happened to it. The stupid golds bonded to each other. So when the gold, how did you get a gold-gold bond in anything? So does that mean that one of these golds is a gold minus and one is a gold plus? Or what this is called is this is a 2 gold zeros. So now, if I want to count these electrons, I can't count this as a gold plus or gold minus in this compound. It's a gold zero. So there's no charge transfer to or from the gold. And if I want to count these things, I end up taking this as a gold zero. And the thing that used to be a 19 electron compound becomes an 18 electron compound because the gold didn't donate anything to anybody. So it's just sitting there as gold metal. And it's a gold-gold bond for gold zero. And that is a very bizarre state of chemistry. And that, I think that got that paper in a nice chemistry journal. Okay. And P.S. is another case of too many trees in the forest here, but this thing is mostly gapped, so it's mostly like an 18 electron semiconductor. But there's one little region in the Brillouin zone where if you calculate Vn2k with spin-order coupling, you get a little crossing over here. So it's almost completely gapped, but not quite completely gapped. And if anybody ever cared to look at this thing, they might discover some interesting topological physics. And Liz and Wei figured this out. In the last couple of minutes, I'll go to things that are more complicated than these. And I know that Daniel and Sergey like early transition elements. I find them to be bizarre. Vanadium is like the god of bizarre transition elements. And this is one we found. It's a homometallic Warwickite. So Warwick is a place in Britain. And I suppose that either the geologists who found this Warwickite were working in Warwick, or this mineral is found in Warwick. But we found one that has only vanadium in it. And nominally, even though there are 2 kinds of vanadium, crystallographically 2 distinct vanadium sites in this crystal structure, they look the same at room temperature. So you get these partial chains of vanadium here. They have one kind of vanadium on the outside of the chain, another kind on the inside of the chain, but they're not very different. And, when I see something like this, I think, oh, come on, they really have to be different somehow. So we did this high resolution synchrotron diffraction at room temperature. And the United States has a wonderful resource, which is called 11BM, which is a beamline at Argonne National Lab, which is a super high resolution synchrotron line. And so it's like the DOE's gift to solid state chemists. It's a lovely thing. So V2O-BO3, which is vanadium borite, has 3 phase transitions on cooling. So not only does it have something, it has something at 200 Kelvin, something at 100 Kelvin, and then something else at that 30 Kelvin or something like that. So there are 3 transitions here on cooling. And so vanadium borate, which has a triangular lattice of vanadium in it that can be, like a little sections of a triangular lattice, has 3 phase transitions on cooling. And I thought, well, how could it possibly have 3 phase transitions? Well, we used the best, highest resolution instrument we could find to do temperature dependent X-ray diffraction in a high resolution synchrotron at Argonne. And this is a comparison of the diffraction pattern. And here you see, first of all, you can see how incredibly high resolution this stupid machine is. And so one set of diffraction peaks doesn't change at all, but another set of diffraction peaks seems to split on cooling first into 2 parts and then into 4. So this crystal structure, which is vanadate, I know that vanadates, so vanadium is from like the first, is like, well, titanium is also interesting, but vanadium is really the god of bizarre behavior. And so I like to call this thing a vanadate on steroids. It's got it goes from some kind of bizarre crystal structure with triangles of vanadium in it to something that separates into chains or trimers or tetramers or hexamers or God knows what as you cool it. And this is for Daniel and Sergey to figure out and tell me what happened. Okay, good luck, guys. Okay, anyway, and vanadates have charge ordering, magnetic ordering. They have charge and magnetic ordering at the same temperature or not. Okay. Okay, I'll just talk for another 3 minutes here and then we can stop. It's a big world and, you know, there's lots of interesting things to do in it. And I want to take the last couple of minutes to introduce this crowd to another thing that I know Daniel and Sergey like and that I like too, and that's hexagonal perovskites. So, you know, Madame Perovska, which was a Russian geologist as far as I know, you know, calcium titanate is the prototype for a lot of lovely materials in the world in terms of practical applications. I think that's the actual perovskite mineral is calcium titanate. And if you put transition metals in there along with electropositive elements and oxygen, you get all sorts of interesting materials. But there's a smaller class of materials that are based on the fact, in my mind, that barium 2+ and oxygen 2- are about the same size. So if you take the closest packing of spheres, which is an extremely stable configuration, and you mix barium in with oxygen, so here's barium 2+ here shown in gray, and oxygen 2- shown here in white. When you mix them together, they can form an ordered lattice. And the ordered lattice has a basic hexagonal shape, which is this motif right here. So this can give rise to all sorts of things. And this is my student who was working on these, Loy Neugen. Again, we do high resolution diffraction on these things. First one we did wasn't so interesting because it had titanium and ruthenium mixed in a hexagonal perovskite. What is interesting about this is that you get these dimers. So if you look sideways to the hexagon now, we have a distinct lattice of things and then a dimer lattice made up of something here. Now, unfortunately, for titanium and ruthenium, they're similar enough that there's disorder in this thing. And so if you have titanium and ruthenium mixed, it's not interesting. What we want to do is make them unmixed. And there are some dimer compounds that are easily made that have been studied by physicists quite a bit. So that's good. But what's interesting to me is when they're bigger. So if you start with this thing as a dimer, a magnetic dimer, and they share faces, you know, you can imagine by the Pauli exclusion principle that you're going to get anti-ferromagnetism here as often as possible because these metals are too close. But once you make 3 of them, then this starts to get more interesting. It starts to look to me more like a molecule in a metal. And now this thing can be interesting. And when you make it with a 3D transition element, I think you can explain the magnetism as Daniel and Sergey did with a localized state. Like the electron, the magnetic electrons are on the manganese. Good, I can explain it. I'm happy. Now, if I go to 4D elements in the trimer, now it's not so clear anymore where the spins are. So now I have 2 ruthenium 4+ and 1 ruthenium 3+, but that's 13 electrons per trimer. And if you look at the orbitals in an isolated trimer, like a molecule, a trimer molecule, you get 1 unpaired electron if you do that. And so this thing is nominally a spin and a half per trimer. So basically, what these things are spin and a half lattice where the spin is delocalized on something that's like a molecule in the shape of a cigar that has spin and a half, 1 unpaired spin on it. So this is a bizarre, it's a lovely kind of magnetic state that you might have of such a thing. And you can actually calculate using regular chemistry calculations which orbitals are occupied or unoccupied in this thing. They're called homos and lumos in chemistry. And so this thing really does look like a molecular magnet. And we're going to go one step further here just before we end. And that is that, you know, so we did a 3D element, we did a 4D element, and now we're going to compare a 4D and a 5D element from the same column. So normally we could do cobalt, rhodium, and iridium. But cobalt is annoying and makes a regular perovskite, so I don't like cobalt. But rhodium and iridium make this hexagonal perovskite with trimers. So you can make these new substances, Ba4NbRH3012 and Ba4NbIr3012. These atoms are right under each other in the periodic table. So in a simple localized picture, they should do the same thing. Okay, now you can say, do they do the same thing or not? Well, maybe they do, maybe not. First of all, you can make the things. So you can dream up that they exist, then you can prove that they exist, and you can make them. And this is why referees make me so mad, because, you know, I take it for granted that we could do it. Here it is. So here's the iridium one. It has 0.8 Bohr magnetons per formula unit with a beautiful Curie-Weiss law. The rhodium one has 1.48 Bohr magnetons per formula unit, and it's got a nice Curie-Weiss law too. You'll recognize these look familiar to you, like from our fluoride paracloids. What is going on here? Where are these magnetic moments? Are they on the trimers or are they on the atoms? Where are they? And why do they have this kind of magnetic moment? The magnetic moment is too big for just a delocalized state and too small for them being localized. Okay, I think we'll end with that, but basically we end up with two things, an iridate version of this trimer, which is a 5D trimer, where the specific heat at low temperature is really bizarre. It goes up to 0.35 Kelvin, which is as low as we can measure it. So this iridium one, you know, the heat capacity of matter should go to 0 at 0 Kelvin. That's one of the rules of thermodynamics. But in magnetic systems that have bizarre magnetic ground states, you can have magnetic entropy left at really, really low temperature. And the iridate has magnetic entropy left in it at 0.3 Kelvin. The rhodium looks more normal, like it's lost its magnetic entropy, but hasn't quite lost all of it. But, you know, the rhodium one is odd because the rhodium is magnetic. So whoever heard of rhodium being magnetic? That's a bizarre state. Okay, good. I think we're going to end. So I hope you could tell that I enjoy this and that I make a living out of listening to what theorists say. And, you know, of course, they have a lot of ideas and insights, and some of them are garbage and some of them are real. So I miss the fact that I can go to conferences and hang out with people, have a beer or whatever. But I think it's fun when things develop in parallel. I think that's going on with these triangular lattice materials right now. And I hope that you could see that a chemical view of electronic and magnetic materials can be valuable in discovering new materials research. And thank you for listening to me for too long, but I had permission to go over, I think. Okay, bye guys, okay.